All right. So today we're going to continue thinking about our veins as we make our way towards tying this all together and starting to think again about blood pressures and what really happens when we're in different environments, when we have different changes in the body. So when we left off, we've been talking about veins. We had talked about how they act as a volume reservoir due to their compliance, right? They're kind of floppy, they can hold lots of blood, but they don't hold much pressure. We had mentioned that veins out in your periphery of your body, they have valves that basically prevent blood from backflowing. These are unidirectional blood flow towards the heart because we define both veins and arteries by their direction, arteries away from the heart, veins back to the heart. Okay. So at the very end of class, we had mentioned that one of the ways that we manage to get blood back to the heart is by using our skeletal muscle as a pump, right? So we don't have all that much of a pressure gradient and we're fighting against gravity, against blood pooling, okay? But we want to keep flow going towards the heart. We don't want flow to go back down towards our feet, let's say. So we have different mechanisms of getting this to work. So we looked at it in this text slide. So when we have skeletal muscle contracting, it squeezes the veins, increasing pressure. As we increase this pressure, blood moves towards the heart. Any blood that's getting squeezed in the opposite direction can't, because it goes back towards the valves block it. When the skeletal muscle relaxes, we then have a low pressure environment in that vein. We have space in that vein and we can have blood go back into the vein between the muscles. So now we have that in picture form, which we didn't look at. So we got an example in the calf here, right? So our valves have a direction, right? That makes this work, right? So these valves are one-way valves. They can open in the correct direction back towards the heart. If we have backflow, right, we would bump into these cusps, just like in our semi-lunar valves when we talked about the heart itself, right? So can't flow back because we bump into the valves, we get blocked. Okay. So as we have this muscle contract, right, we have a vein that's running through it or next to it that gets compressed because that muscle bulges, right? So we can see that as this muscle contracts, right, we see that bulge. So it's squeezing the center of the vein here. So that remaining blood that was in here is getting squeezed in this direction. Some of it might be getting squeezed in this direction, but that doesn't matter because we have this valve. Okay. We do have a valve on the other side, but the blood that is getting squeezed in the correct direction is allowed to flow through because these valves are one way, right? And we can see that we have some anatomical terminology on here as well. So proximal would mean basically back towards the heart, right? Proximal means nearer in towards the center of the body. Distal means far out, away, distant, right? So it's that one that's distal, right? That farther away one that has to close to prevent blood from flowing through the veins back towards those distal parts of your limb. Here we see that relaxation state, right? So during the relaxation state, basically we're thinking kind of about this next segment, right? So that proximal valve closes, right? A little bit now that the volume is here. we relax, so this tube is open and now it's low pressure because we just squeezed a bunch of blood out. So now, because we've got the space to move to, we've got a low pressure environment here because all the blood just escaped. We have movement from higher pressure to lower pressure, so almost kind of created a vacuum in here, right? So now this distal valve opens and blood moves up into this space in between the muscles and the cycle can repeat. So this is our skeletal muscle pump. And so how we use movement of our body to help us get blood flow back to the heart. Questions about this part? So we're going to talk about another pump. So it's not just the skeletal muscle pump that helps us move blood back towards the heart, but we need to think a little bit first about what happens when we breathe, because our next pump is called the respiratory pump. Respiratory has to do with breathing. Yeah, in this case. Okay. So your thorax is basically your chest, right? It's some orientation for this question, right? Thorax is your chest, right? Your diaphragm sits like below your ribs, okay? And what happens when you breathe in is that diaphragm essentially moves down, right? Really what it's doing is flattening, but you can think of it as moving down and creating more empty space in your chest when you're breathing, okay? As you start to breathe in. When you breathe out, when you exhale, we'll talk about this in our next unit, right? The diaphragm changes shape, basically pushing this space up, right? Less space in your chest, everything's more compressed. And that's why you start to exhale. That's why you start to lift out. So as we think about this, what kind of pressure are we creating here as we start to inhale? At the beginning of inhalation, in the chest, do we have a lot of pressure or a little pressure as we're just about to breathe in? Is this a low pressure environment or a high pressure environment? And we've suddenly created this big empty space.
Well,
Yeah, exactly. So it's a low pressure environment because we've created this extra room, this extra space, right? So this is kind of like in the last one, I was saying that we created kind of a vacuum by squeezing all the blood out, right? And then when we relax, we've got that space to fill into. This is the same thing that happens as your diaphragm moves when you breathe. This is also, we'll see why air goes into your lungs, because you create this low pressure environment by changing the size of that thorax, changing the amount of space you have there. But this also affects the blood, which is why I'm mentioning it now, right? So we're creating this low pressure in the chest. And when we breathe out, we create this higher pressure in the chest, which is what forces the air out as well. So that's important for understanding what's going on when we think about the respiratory pump, right? So inspiration, breathing in, what is fundamentally happening in order to suck air in? We're making a big space in the thorax, which means we're making a low pressure environment. So that does suck air into your lungs, but it also has an effect on the blood, right? Because it's just a general low pressure environment. It's not specific about lung tissue or blood vessels or anything in particular. So that low pressure environment is also kind of pulling on the blood in your abdominal cavity, right? Because we suddenly have low pressure here. We know everything moves from high pressure to low pressure. So if we have really low pressure here in the thorax, pulling blood up towards the chest and therefore towards the heart. And we also have a point at which we're squeezing, right? Because your diaphragm is dividing your thorax from your abdomen, right? So it's basically like normal terms, right? Like it's making the space For your chest, larger, but that squeezes down, leaves less room for all the abdominal organisms, right? So this belly region is getting smaller, it's getting compressed. So we've created low pressure in the thorax. And conversely, we've created higher pressure in the abdomen. So as we create this higher pressure in the abdomen, right, this is creating pressure on those veins in the abdomen. So any blood that's in your abdomen now is under high pressure. It's low pressure in the thorax, right? So we have a much stronger gradient than we would otherwise for that blood to return to the heart, because it's going to go from that high pressure abdomen to the low pressure thorax as you start to breathe in, right? So this is why we call it a respiratory pump, because it's relying on you breathing in and out, right? On that respiration, right? So it's not going to be consistent all the time your chest is sucking blood towards it. We need this movement and this change in pressure to power this pump. But it does help us get blood back to the heart. So overall, our effect here is that we end up increasing our central venous pressure. So we end up increasing how much blood we have here in the chest because we're sucking it up, and then the pressure right after we suck it up. And so that then increases how much blood ends up going back to the right side of the heart. Because if we have more pressure in these veins going into the heart as we start to breathe out, right? That's now going to go into the heart, into that low pressure atrium, right? Atrium. Right. And so this is how we're kind of powering the return of blood to the heart so that we can do this whole process over again. So big picture, for our veins to return blood to the heart, we actually kind of need movement to help us along because we have this kind of overall lowish pressure system. So we use temporary increases in pressure caused by contraction of skeletal muscle, the skeletal muscle pump, and caused by changing pressures in the thorax and abdomen, respiratory pump, to pull blood back towards the heart, to increase pressure in those veins right next to the heart once we get the blood there, which then helps us fill the heart with that venous blood. So that's overall how the system works, how we get blood. So we have a picture here just comparing those two things. So you can also see here that relationship between the thorax and abdomen. Right, so the diaphragm is here, right? So when you have more space here, we have lower pressure in the thorax, higher pressure in the abdomen. So we have the movement of blood up towards that lower pressure thorax. Okay. Then when you breathe out, right, we're now creating a lower pressure in the abdomen, a higher pressure in the chest, in the thorax, but our blood just already traveled into the thorax, right? So it's not going to go back to the abdomen. Instead of going back to the abdomen, the blood that we have here now, that's now under increased pressure, getting squeezed, it's going to get squeezed into the heart itself. That's what's going on with the respiratory pump. Questions about the respiratory? I know that does rely on this respiration stuff that we haven't talked about yet. All right. So, two ways we can change our pressure in our veins and therefore change venous return being venous blood returning to the heart, right? So more blood back to the heart. We can also change blood volume. So if we have increases in blood volume, we're going to see increases in venous pressure. Just more blood in those veins is going to increase their pressure. if we have decreased blood volume, so just less blood in our bodies, right? We're gonna have less pressure in the veins, right? So if we don't have enough pressure in the veins, it's gonna be hard to get that blood ultimately back into the heart because we have that trade-off, right? The heart also has to kind of suck blood in because the heart has to have those atria at lower pressure than higher pressure in the veins right there where they join. This is actually how we are going to kind of long-term regulate blood pressure. And so short-term, we're going to see a bunch of nervous stuff going on, like your little nerves, helping us regulate our blood pressure. But in the long term, we're actually going to end up involving the kidneys as well. The kidneys are going to help us change the amount of blood, especially in the veins. But therefore also going through the system as a whole, therefore long-term changing your blood pressure. I think this is the last one we're going to talk about. But venomotor tone also can affect the pressure in the veins, right? And what this has to do with this compliance concept that we talked about. So a reminder of the compliance. Right. So what we have happening here, the difference between our arteries with their low compliance, right, was it took a low amount of volume to create a pressure versus veins with their high compliance takes a higher amount of volume to create that pressure, right? Or we can read it the other way as well. So this is how that's showing us to read this chart on here, but we could do the reverse, right? And if we wanted to say, okay, for a specific volume now, right? So I'm going to write a new volume. Let's make it volume 3, right? So actually I need it to intersect both lines. So I drew that too high. Sorry, everybody. And I'll just draw this one over. Okay. So for a given volume, right? Say this number is like 3, right? It's some actual volume, right? So volume of blood, if it's in a vein, is creating low pressure, but that same exact volume, if it's in an artery, creates high pressure. So what compliance is a measure of the relationship between volume and pressure. Right? So we can think about the influence of volume on pressure, or we can think about the influence of pressure on volume. It works both ways because it's a relationship. So exactly how you state it depends which of those two things you're focusing on. Right. So this gets to the venomotor tone. We talked about tone, right? Smooth muscle has a little bit of tension, right? It's not totally contracted. It's not out as loose and big, wide diameter as it could be. Okay? So venomotor tone, we see it increase. What an increase of venomotor tone is, it's basically like vasoconstriction, but in a vein specifically. All right, so an increase in venomotor tone means that we have a little bit of contraction kind of going on, right? So when the smooth muscle in the wall of that vein contracts, right, it gets a little bit smaller, right? So that's our increase in venomotor tone, which therefore is going to affect how compliant it is, how easily it can hold that volume of blood. It's not so big and floppy anymore, right? So this creates more pressure. If we increase that venomotor tone, because we've got less space, the walls are less floppy, right? More pressure. Another way of stating what we're doing here is that we decreased compliance because now those walls aren't just like holding lots of volume and not creating any pressure. They're creating a little more pressure and they're not holding as much volume, right? So this overall is going to have the result of increasing venous return to the heart, because when this is happening, like pick a specific thing, right? Like your vena cava going back to the heart, right? If you're increasing the central venous pressure, you're saying we're increasing pressure in the vena cava going back to the right atrium. we're now creating a pressure gradient between that vena cava, higher pressure, lower pressure in the right atrium. So we're increasing flow back to the heart in that right atrium. So when we're thinking through how blood is returning to the heart, we might want to think about it in different steps, right? You might want to separate it in your minds, like, okay, how are we getting that blood back up to the chest? And then make sure to add on that second step of like, okay, how do we get that blood that's in the chest back to the heart? And that'll get you from thinking about those skeletal muscle pumps and respiratory pumps, which are going to help us get blood kind of back into the thorax, and then add on what is the point of this venous pressure stuff and how does that relate to getting blood back into the heart. Okay, so we're going to walk through kind of a flow chart of all the various things relating to our veins that are ultimately going to have an effect on our mean arterial pressure, so our weighted average blood pressure. So let's start out at the top. Okay. We're actually going to start by thinking about the sympathetic nerves, right? So we had, actually skipped over it, but there was a comment on here, right? So that smooth muscle in the veins, just like in our arterioles, is from the sympathetic nervous system. It's responding to that sympathetic nervous system. It's got those alpha adrenergic receptors that we saw out throughout our arterioles, kind of everywhere in the body. We don't have to worry about the beta 2 receptors here. Okay, so what we're tracing through here, say we start with your sympathetic nervous system getting really active, right? So you're really stressed out, you're getting ready for fight or flight, right? Your sympathetic nervous system really active, making lots of norepinephrine, right? That norepinephrine going to bind to alpha receptors in those veins, so that smooth muscle, right? When it does that, they tense up a little bit more. We refer formally to that tensing up as an increase in venomotor tone. And so we tensed up, we've increased venomotor tone. Okay. We have a decrease in compliance, right? So we saw that we had that relationship between volume and pressure that we describe as compliance. So usually in our big floppy state of the vein, we're up here, right? So a specific volume creates a specific pressure, okay? Now, when we're all tensed up, when we have this increase in venomotor tone, we're lowering the compliance, right? Which means that we can hold less volume for a given pressure, or read conversely from the opposite side, right? If we want to hold, if we want to hold that same amount of blood, I'm gonna have to draw my blue line eventually going up that light one so that we can cross that barrier. Sorry, everybody. Needs to intersect both lines, because what we're going to notice here, right, is that if we keep that same volume of blood here, right, it creates low pressure in a highly compliant vein, but it creates a higher pressure in this vein that now has lower compliance due to an increase in venomotor tone. Okay. So I actually find it quite helpful to just like draw that drawing as I'm trying to think through compliance, right? Because then you can kind of just read it to yourself in both directions. So that we have this drop in compliance, right? So drop in compliance, we have whatever volume we had. So it was under low pressure before. Now we have a drop in compliance. So now it's under higher pressure, okay? Which is how we see high pressure now in the veins, okay? Because of that drop in compliance due to this increase in venomotor tone. We have three other ways that we might end up with that high venous pressure. And in practice, they're all kind of going to be happening at once, right? So as your sympathetic nervous system is activating this fight or flight response, at the same time, you're probably going to start moving your muscles. So those muscles are going to start pumping that venous blood back up towards the thorax, increasing the venous pressure, right? So we've got this return basically up to those central veins as our skeletal muscle pump is working. When your sympathetic nervous system is active, you also actually breathe faster, right? Potentially harder, but definitely faster, right? So our respiratory pump, as you're breathing faster, is also increasing, therefore, how much blood it's pulling back to the thorax, and therefore how much pressure we have in those veins that are coming up towards the heart. And we'd also probably have some hormonal signals that increase blood volume, but this tends to be more related to longer term regulation. But it's a factor that would have the same effect. So it's on this chart too. These are all ways that we would increase venous pressure. If we want to change smooth muscle, we've got to use the sympathetic nervous system. The other ones kind of pretty directly do it. Okay. When we have an increase in venous pressure, what we have happening, we got our heart. This is our right atrium. And I'm going to give us a vein. Cool. Okay. So if we've just created high pressure in this vein returning to the heart, we've created a system where we have lots of blood go back into the right atrium. So we can think of this as kind of like timestamp 1, so that we can understand this next thing on the flow chart. Is at timestamp 2, after we have that blood come back to the heart. Okay. All right. So we had more blood come back to the heart, more venous return. We now have a higher pressure in the atrium than when we only had a little blood coming back when we were like relaxed and your sympathetic nervous system wasn't so active. So that's why this high venous return is creating this high pressure in the atrium. Okay. So next, this affects our end diastolic pressure, which we also refer to as preload. So all that is right, like while your heart is filling, it's filling while it's relaxed, right? Diastole is when your heart is relaxed. So we're filling with blood at the end of that relaxation as we're having that blood go into the atrium and into that right ventricle, right? More blood in the heart, more blood at the end of that relaxation part, at the end of that filling part, means more pressure, because pressure and volume are directly related. If you have more volume in that same space, you have more pressure. So we increase our end diastolic pressure, or our preload, which means we are also increasing the end diastolic volume, EDV, which we saw in some of our calculations in our heart unit, right? So we both have more pressure at the end of diastole, and we also literally have more volume of blood in the heart at the end of diastole, which means that when the heart contracts during systole, right, to contract it back down, squeeze the blood out, there is more blood in there, so we can squeeze more out. So we see an increase in stroke volume in response to these changes that we've created to the pressures in the heart that are all due in this figure to just a couple of changes in the state of our veins. So we've changed our stroke volume. Okay. An increase in stroke volume is going to create an increase in cardiac output, right? Because cardiac output is our stroke volume. So the amount of blood per heartbeat times our heart rate, right? So the number of heartbeats per minute. Okay, so if we increase stroke volume, we increase cardiac output. We saw in ANP1, right, that we also affected that stroke volume by directly affecting the cardiac muscle tissue, right? Now we're affecting cardiac output, still of the sympathetic nervous system, but super indirectly by controlling our veins, right? But it's having kind of a synergistic effect here, doing the same thing. Okay. Overall, we're going to end up with an increase in our mean arterial pressure because we have our relationship between flow and pressure difference, right? So we saw that our flow is our cardiac output in our system overall. Our difference in pressure is really going to end up due to that mean arterial pressure. And we need to think about our resistance, which comes from our total peripheral resistance. Okay. So we can reshape that, right? Take that resistance and multiply it by our cardiac output. And that gives us an equation for our mean arterial pressure. So this is how we can tell that the overall effect of increasing that cardiac output, absent any changes in resistance, would increase our mean arterial pressure. That's a lot of information distilled into this one single flow chart. Right, so we're tracing all the way from what's going on with veins, all the way to how are we affecting the blood pressure. So, questions about any of these steps? Takes a fair amount of like slow thinking. I do recommend spending some time practicing, thinking through this stuff, right? You might try hovering over like the arrows on this stuff and making sure that you can logic out for yourselves, like, okay, so what does it really mean if we see a change in our compliance? What is the effect going to be on the pressure in our veins? So that would be a thing to try testing yourselves on after you spend some time slowly going through and digesting stuff. Okay. I'm going to ask you a more simple question rather than an interpretation question here. So I just want you to let me know which of these things on this list are going to increase venous return and increase cardiac output. And you can select as many as happen to be true. Right, take another couple seconds to finalize your answers. Okay, cool. Yeah, so almost all of these are true, right? So first things first, anything that increases venous return is going to increase cardiac output. So anytime you get more blood back to the heart, we're going to increase how much blood the heart puts out, right? Okay. So you're not going to have the case where we have a mismatch between the venous return and the cardiac output. And we can do that by changing lots and lots of things about our veins. So we can change the activity of either of our pumps. Those pumps work harder, we get more blood back towards the heart, right? Increased venous return, therefore increased cardiac output. So that's both these first two, the muscle pump and the respiratory pump. Okay. If we increase the blood volume, increase the amount of blood that is going to end up in your veins, because 60% of the blood comes down in the veins, right? There's more blood in the veins, that blood's taking up more space, which means we have higher pressure, which means we see an increase in the venous return. So more blood goes back to the heart, because that heart is filling due to a pressure gradient between the vein and the heart. Okay. And one of the ways that we can affect pressure in the veins, other than affecting that volume, is affecting the behavior of the walls of the veins, right? So we're changing compliance. We're not increasing it, we're decreasing it. Right? So when we tense them up, that's a decrease in compliance. That's why the increase in venous compliance is wrong. So we want to decrease. And the way we would have created that decrease in venous compliance would have been by increasing our sympathetic activity, which increases our venomotor tone, which creates the decrease in compliance. So all of these are summarized in that previous chart. I'm going to spend a little bit of time breaking into our lymph and some of our regulation of blood pressure. We'll spend more time on this regulation of MAP next week, but we'll break into it. So, what we want to know for the perspective of our cardiovascular system, right, is that your lymphatic system runs like alongside your blood. Okay, so your lymphatic system also has vessels, right? It's got tubes. It also has nodes, right? Like we have lymph nodes, we even have lymph organs. So it's doing its own specialized stuff. In addition to its job that is relevant to us right now, which is to return filtrate, excess filtrate, just fluid, plus all the other stuff that's in plasma except for our proteins, right? So that fluid-free plasma that we talked about when we looked at our net filtration pressure, right? On net, we had 3 liters moving back into the tissue, right? And it didn't go back into a vein, right? At that point, when we were in the capillaries, but we don't want to just have all the tissue swelling with that fluid and have it never go back to the heart. So this is where we need our lymph system. Okay. So the lymphatic system is going to have parts of itself that are open there right next to the capillaries. They're going to help us take that filtrate and ultimately return that fluid to our circulation. Okay. So we're going to have essentially like lymphatic capillaries. So they're soaking up that extra fluid that we transported, that we filtered into that interstitial space, into their own kind of capillaries. Your lymphatic veins, your lymphatic vessels are associated with your veins. So they do, some of them dump into veins, and some of them dump into something called the thoracic duct, which is just the name for one of our particular lymphatic vessels, our lymphatic tube. That thoracic duct empties into the right atrium, which is where our veins are dumping their venous deoxygenated blood, right? So it's basically mixing in with all that deoxygenated blood. So we've returned the fluid to that heart, to that same place, that right atrium. Lymph basically moves through the lymphatic veins, right? So the tubes running back towards the heart, the same way as blood flows through regular veins. So we're not going to concentrate on them specifically in any way. So this is the portion lymph that has to do with things like It's partially why lymph is related to like swelling, right? But also, right, this is how we just functionally make sure that we keep fluid balance, we keep all that fluid going through our cardiovascular system. And we're not dropping our amount of blood in the cardiovascular system as we filter out plasma in the capillaries. Their immune system component has to do with immune cells that are located within the lymphatic system. Specifically, it's got a bunch of macrophages in there. And I think we'll talk about those in Phys Lab more extensively, and we'll touch on them when we talk about like the parts of blood. So here's what that all looks like, right? So you see our normal cardiovascular system in the center here with our right and left sides and our red and blue colors, right? So we have our arteries going away to our capillaries, right? So this is where we would have that net filtration pressure. On net, we have filtration, and on net, we have filtration of 3 liters per day. Okay, so we're ending up with extra fluid here in this space next to the capillaries. Whatever's left, that lowered amount, is going back to the heart, right? To make sure that we don't drop in fluid levels in the plasma overall as we like go minute to minute, hour to hour. We have lymphatic capillaries next to our normal capillary beds from the systemic circuit. They have tubes, the lymphatic veins. That's what we refer to these as, right? So the lymphatic veins also have valves, just like our normal veins did. Okay. Some of these are dumping back into our normal veins right here as you go into the heart, and some go into the right atrium itself. Ultimately, we get all that fluid back to the right atrium, back into the blood, back into the plasma. So we're mixing it all back together again. Okay. That's pretty much all we need to know about lymph for, I'm gonna stick this one, for the purposes of this course. Okay. Sorry, for the purposes of this unit. We'll talk about lymph once more. So next, the big topic is the regulation of MAP. So the regulation ultimately of blood pressure. Okay. So as we were going through that flow chart, I showed you how we get from that initial flow equation, right? Our flow being equal to a difference in pressure over resistance, plus the fact that we know that cardiac output is equivalent to our stroke volume, the amount of blood that we're squeezing out of the heart, each heartbeat, times, it's too much like a plus, sorry, times our heart rate, so number of heartbeats per minute. Right, so we can combine these two equations because cardiac output and flow are the same thing for our purposes to get that equation for MAP, where we have our mean arterial pressure equivalent to, we'll keep the stroke volume right here. All right, we'll keep this heart rate right here. All right. But what we're doing now is we've moved our resistance over, right, and multiplied it by that flow, which is why we're adding in our total peripheral resistance. All right. So these are the 3 factors that are going to affect our mean arterial pressure. Now, we can affect our blood pressure through our nervous system, right? So we're going to have neural control of our blood pressure, right? Which we can already kind of think about, right? We talked about the sympathetic nervous system affecting the heart itself, right? So we saw at the end of AMP1 that the sympathetic nervous system increases heart rate and it increases stroke volume, right? Now that we've talked about our blood vessels, right, we know that especially when we're talking about our arterioles, right, the sympathetic nervous system affects smooth muscle as well, which means it affects arteriolar radius and therefore arteriolar resistance, which is mainly what we're adding up to get our total peripheral resistance. So we already have some kind of idea about how nerves could affect our mean arterial pressure, like what that mechanism is going to look like. We can also affect our mean arterial pressure through hormonal control. And so we already know that when we think about the sympathetic nervous system, we always end up talking about epinephrine as well, which is a hormone, right? And we have some other hormones that have similar effects. And in terms of long-term regulation, we'll think about the kidneys, and those are going to be under hormonal control as well. Okay. The first step, though, to regulating your blood pressure, is fixing your blood pressure. One of the most common situations we think about is how do we fix it if we have a sudden drop in blood pressure, right? So like whenever you stand up, your blood tries to rush to your feet, right? And we want to fix that. We want to keep the blood pressure up. We want to keep blood going to the heart. We want to keep the heart pumping blood. But we also might want to fix low pressure, like if you have a horrible cut, right, and you're kind of like bleeding out, you do want to kind of try to keep blood pressure up so that you can keep blood flowing to all your organs, because we need that blood pressure, we need that map to create a pressure difference so that we can continue blood flow to all our organs, right? All these equations are relationships, right? So our cardiac output affects our mean arterial pressure, but the other thing is also true, right? Our mean arterial pressure also affects the flow to our organs. So when we start out next time, we'll be thinking about our receptors, baroreceptors, that sense low pressure is going to be related often to low volume. Yeah.